Okay, so we just finished that combining ratios worksheet or those activities, and we figured out that some combinations of elements seem consistent. If they're down one group, so one column of the periodic table, some of them mix nicely with another column in a similar ratio every time. So we're going to use this pattern to figure out some charges on some other things as well. So let's play with this today. But before we do, we have to figure out. So our goal is how do we write an ionic formula? So ionic formulas contain a metal and a nonmetal. That's a base need. We need to know this. Then we have molecular compounds. That's not what we're talking about today. Those contain only nonmetals. So the ionic compounds, that's where we have a cation, which is positive, and we also have the anions, which are the negative components. The compounds have to be neutral. The positives have to equal the same amount of negatives. They're going to mix together to make a neutral compound. So let's just try this out real quick. So for this atom up here, so this one right here in this bubble, how many positives must that cookie dough be for it to be neutral? I have 4 chocolate chips. Those are negatives. Those are the electrons. Those are the only things that can move. So it has to be 4. There has to be, this cookie dough has to have a charge of 4 plus. It has to be positive 4 times in order to equal this. Okay? So when we have an ionic bond, it's also important to know, as I mentioned, that the electrons are the things that are moving. That's what's creating these charges. And we can have a varied amount, right? So sodium, for example, when it gets together with chlorine, they come together and chlorine takes one of those electrons from sodium. So we end up with Na plus and Cl minus. So the metals are giving those electrons to the nonmetals. And we found this pattern throughout the periodic table. So remember, these are the annotations that I want you to have. I want you to be able to know which are the metals, the white parts here, which are the nonmetals, the yellows, which ones are the metalloids, these ones that I put in green. And then I wanted you to put the charges that we found. So anything down this group, right here, has a charge of +1. Everything down this group has a charge of +2. This means that it gives away 2 electrons. Over here we have this -1. This means that each one of these like to gain 1 electron. We have this -2, which means that these things like to gain 2 electrons. And this column right here, 3 electrons. Okay? Those are my really important ones. We need to understand these two are losing a consistent amount of electrons. This is losing 1 electron. This is losing 2 electrons. This is gaining 1, gaining 2, gaining 3. Okay? So let's try to make this. So if we know that they have to be neutral, we can figure out what the formula is. So let's take a quick peek at what these are. So we got lithium and fluorine. So I go back to my chart and I find lithium. Lithium's right here in group 1. That's a +1. And fluorine over here is a -1. Okay, so what I like to do is write them right underneath. So lithium is a +1 and fluorine is a -1. And now I just check, are they balanced? So this +1 right here matches this one. It's perfect. I can pull them down together. So I have LiF. And that's my formula for this side. Okay? Now, over here for K and O. So let's look at potassium and oxygen. So potassium's right here. Again, that's in my +1 column. And then oxygen, which is over here, is a -2. So let's add in our charges here. So we will put that this is a +1. and this is a minus 2. So we can already see that these are not balanced. So how many of these would I need to make it a minus 2? I would need 2 of them. That's how I can get them to equal each other. So now I know there's a 2, so I need 2 of these potassiums, so that's K with that little subscript to say that I have 2, right? And then just 1 oxygen, so K2O. That's my formula here. Okay. And then lastly, let's try one more. We have rubidium and nitrogen. And so rubidium, again, that's in my +1 category over here. And we're adding it to nitrogen, which is a -3 in that category. So we can make a guess. We can figure this out, right? So how many of these rubidiums do I need to equal 1 nitrogen? I need 3. So same thing. I'm going to bring down this RB. I'm going to place this 3 right here. That's the subscript, right? And then I'm going to bring my N down, right? So we end up with that RB3N. So it's important that subscript is always talking about the 1 in front of it. So if you think about it, I always like to do this just to double check. It does that. So it's right in front. Okay? So let's try this with a different group. So all of those were through group 1. Let's try this with group 2. So group 2, meaning this group right here. So we got magnesium. Magnesium is a 2. So magnesium over here is a +2. Fluorine over here, which we did a minute ago, is a -1. Okay? They're not balanced. This is less. How many would I need? I would need 2. So we have MgF2. Again, bringing that 2 with the F down in that subscript spot. Let's look at Ca. Ca is over here, it's still in group 2. So that ends up being a +2. It's a metal, loses electrons. We got our nonmetal oxygen, which gains 2 electrons, so it's a -2. They're balanced, they're perfect. Let's keep moving. CaO. Then let's look at over here, we got strontium, and we also have nitrogen. So we have strontium, which has a +2. And then we have nitrogen, which is our -3 again, right? It's in this column right here. And we got a bit of a problem. This one isn't as easy. So what is a number that we can get them to match in, right? That is close. So what charge can we get both of these to equal that's fairly close? And if we look at it, we have 2 and 3. So what's a number that both 2 and 3 go into that would equal this out? So if this weighed 2 pounds and this weighed 3 pounds, how would I equal it out on the scale? What would I need? Well, they both go into 6. So if I have 3 of these, I'll have a +6. If I have 2 of these, I'll have a -6. So you can see the total charges here. So if we're doing the math, 3 times 2 is 6. 2 times 3 is 6. We can get that to equal each other. And again, we're going to bring down that number that we put out front. So SR3, we have N2. And those charges are equal. They're now neutral. There's an equal amount of positives and negatives. Now let's try something that's a little more challenging. We're going to mix these up a little bit. So I've got CS and I've got S. So let's look at where they are. So CS is in that +1 column. S is over here in this -2 column. Pause the video if you need time to follow along. And we're going to see how we can balance them. This is a 1, this is a 2. The lowest number that they both go into is 2. So how do I make that a 2? I put a 2 up front. So we got CS2. 2, S. Then we got Be and Br. So we got beryllium and bromine. So beryllium is right here. That has a +2. Bromine over here has a -1. So how do I get them to match? Be is fine, right? Br, I can add another one here. So that's 2. So Be, Br2. And then last but not least, we'll look at potassium and selenium. So we have potassium over here. That's a +1. We have selenium, which is a -2. And similar to the other ones, right? So I would need 2 of these. So it would be K2SE. And nice and equal. Okay, now what if we don't know one of the charges? So these are not in our categories, right? These are what we call transition metals. They're in this no man's land in the middle here. So we're going to try to find out what charge they are, because they're given to you as a formula, and we know they have to be neutral. So if I have iron, that's in my weird, it's not on one of my columns. So we have Fe, we don't know what that is. And there's one of them. And then I have Cl, and I have 3 of them. That's under my -1 category. So I have 3 of these with a -1. I know that. This one has to be, there's only one. So how do I get this to equal each other? Both sides have to be equal. Well, the only way is if this is a 3+. So that charge on that Fe, this actually would break down into Fe3+, and this would break down into 3 Cl minuses. So we can break it down even further. Now let's look at another one. Let's look at mercury. So mercury again is down in this weird column over here, right? Mercury is right here. It's not under one of my numbered columns. We look over to O. So Hg, there's only one of them, and we don't know what that charge is. But O, we know we have one O, and it's a -2. So the only way this works is if that Hg, right, has a +2 charge on it, and that O has that -2 charge on it. So then let's look at one more. So now I have Hg2O, which this is why they're called transition metals, because they can actually have different states of charges, right? They can have different amounts of a positive charge to them. So let's look at what we got. So we know we have one O again, and it's -2. Nothing has changed with that. It has to equal 2 of these mercuries. The only way that this will work is if it's a +1. Okay? So that means that each one of these, I have 2 of these Hgs +1, and it equals oxygen, which has that -2 charge on it, right? So that's what's going on. Those charges are equal. We have a nice solid state there of a neutral atom, or, well, neutral molecule, right? Because actually, we can't even call it a molecule. It's a compound. So it is an ionic compound, right? There we go. So let's keep that in mind as we keep working. Good job, everyone.